Hello, this is our last video on integration, and what we're going to do is we're going to talk about substitution and integration by parts, which are certainly methods that you have learned when you were dealing with the single variable calculus. Most of the times when you were finding an integral, you would use some sort of substitution and sometimes also integration by parts. So we're going to state these theorems and then we're going to prove them, and we will carefully do a couple of examples. Okay, so here is the first theorem. This is integration by substitution. And make sure that anytime you're using these theorems, you check all of the conditions. Of course, that is true for any theorem in mathematics. Anytime you're using a theorem, you have to first check all of the conditions. Let f from ab to r and phi from cd to r be continuous functions whose derivative of phi is bounded and continuous. And we are able to say that phi of CD is inside AB. The reason we do that is that we want to be able to, in fact, do the composition of these two functions. Then we have this equality. So since we are dealing with integrals, it would make sense to differentiate both sides and show that and use the identity criterion. So let's in fact do that. So consider this function. Consider f of x equals integral from c to x f of phi of t. I will use t here, phi prime of t dt, minus integral from phi of c to phi of x f of t dt for all x inside c to d. Notice that if you take the derivative of this function, f prime of x becomes f of phi of x times phi prime of x minus, the second one is also the same. It would be f of phi of x times phi prime of x. So, and the reason is a theorem that we had learned before. So now, if we have to check the conditions of that theorem. So note that the conditions were all satisfied. Note that f and phi prime are continuous and bounded, and phi of CD is inside AB, which is why we are able to do the composition. So by the identity criterion, f of x is equal to a constant. Let me call that perhaps alpha over the interval from c to d. Now, if you plug in c for x, if you look at f of c, we would get integral from c to c, or integral from c to c f of phi of t times phi prime of t dt minus integral from phi of c to phi of c if you substitute x by c, and this is f of t dt, which is of course integral from c to c is 0, integral from phi of c to phi of c is, and this should be c, phi of c to phi of c is also 0, so the whole thing becomes 0. So because f is a constant over over the whole interval and it's 0 at one point, that means f of x is equal to 0 for every x inside the interval from c to d. And that completes the proof, because we wanted to show the difference of the two sides is 0. Okay, so that's the first theorem, integration by substitution. The second theorem we're going to prove today is what we call the integration by parts, and as I said, you have certainly used that extensively in single variable calculus. So suppose you have two functions f and g, both are continuous and their derivatives are bounded and continuous. Then we have integral of fg prime is, this is like the integral of u dv equals uv minus integral of v du. Integral u dv is uv minus integral v du. That's the way you see that in single variable calculus. So this would be, since it's a definite integral, you have to evaluate it at the endpoints. This would be like u dv, this would be v du. Okay, so let's prove this one. The proof would be, if you combine the two terms, the two integrals, we would be able to use the product rule, and then we can split that up into two different integrals using additivity. However, in order to be able to do that, I will have to use the fact that these functions are in fact integrable. So I will have to prove that. So note that by extreme value theorem, f and g are bounded also by assumption f prime and g prime are bounded. Thus, there are real numbers a, b, c, d such that f of x is less than or equal to a, g of x is less than or equal to b, and in fact we can take a, b, c, d all the same because we just take the maximum of these, and f prime of x less than or equal to c and g prime of x less than or equal to d for every x inside the interval a to b, although because we are dealing with derivatives I will have to look at the open interval rather than the closed interval. So that means if I look at fg prime, this would be fg prime at every point would be in fact less than or equal to AD, and f prime g at every point would be less than or equal to BC. And if I look at fg prime plus f prime g at every point by triangle inequality, that would be less than or equal to AD plus BC. This is for every x inside the interval a to b. Thus, fg prime, f prime g, and fg prime, f prime g are all bounded. Since f and g and f prime and g prime are also continuous over the open interval. So we have four continuous functions over the open interval. Any product of them or sum of them is also going to be continuous over the open interval AB. So are fg prime, f prime g, and their sum, fg prime plus f prime g. So by a theorem, fg prime, f prime g, and fg prime plus f prime g are integrable. So that means these are integrable. So I can rewrite this. I can write down the integral from a to b of fg prime plus f prime g as integral from a to b of fg prime plus f prime g by additivity. However, note that the left side is in fact, the right side is the sum that we wanted. The left side is integral from a to b of fg prime plus f prime g is in fact the integral from a to b of the derivative of fg by product rule. Now, since the integrand is continuous, I can use the first fundamental theorem. This would be fg evaluated at b minus fg evaluated at a by the first fundamental theorem. First fundamental theorem told us integral of derivative would be the integrand. And if you combine these, we get exactly what we wanted. Therefore, integral from a to b, so if you combine the two things that we got, integral from a to b of fg prime plus integral from a to b of f prime g is equal to this bottom, which is f of b g of b minus f of a g of a. And that's exactly what we wanted to prove. If you just move the integral of f prime g to the right, you get exactly the identity that we were given. Okay, so this proves the integration by parts. Integration by parts follows from product rule. Product rule, additivity, and first fundamental theorem. Okay, so the last thing we're going to talk about is a couple of examples. So normally, if you were to do integral of natural log of x, you would do integration by parts. This is the way you would have done it in single variable calculus. You would have taken u equals natural log of x, dv equals dx, du equals 1 over x dx, and v equals x, and you went from there. So we're going to do the same thing, except that we have to make sure that we check all of the conditions. So the two functions that we take are going to be natural log and x. So let f of x be natural log of x and g of x be x in the integration by parts. Note that f and g are continuous on 1, e, and f prime, which is 1 over x, g prime, which is 1, are continuous and of course bounded on 1, e. So therefore, we can apply the first fundament. We can apply the integration by parts. So the integral from 1 to e of f times g prime, which is a natural log of x, times 1 is equal to natural log of e times e minus natural log of 1 times 1 minus integral from 1 to e derivative of f, which is 1 over x, times g dx. This is the integration by parts. So this would be natural log of e is 1, so that's e. Natural log of 1 is 0, so that's e minus integral from 1 to e of 1 dx. And we can evaluate this one. So this is something we have done before. e minus 1, which is going to be 1. Okay, so that's the first example. If you look at the second example, normally what you would have done would have been by substitution. So what you would do is you would take u equals x squared plus 1. That would be our function. So I'm gonna put the solution like the single variable calculus solution on the right. U would be x squared plus 1, du would be 2x dx, and then you rewrite that integral in that form. So we're going to look at this u. This would be let f of x be, so the function that we have is 1 over x, and phi of x is going to be x squared plus 1. Note that phi prime of x is equal to 2x is continuous over the entire real line. So it doesn't actually matter what value, what interval we're looking at. So it's continuous everywhere. So now we're going to have to look at phi of 0, 1, which was the interval that they gave us. Phi of 0, 1 would be inside. When you plug in 0, you get 1. You get like 1, 2. And this is inside the domain of this function, inside like 0 to infinity. So f is continuous on the interval 0 to infinity. So we can use the substitution. So the integral from 0 to 1 of f of phi of x times phi prime of x dx is equal to integral from phi of 0 to phi of 1 f of x dx. So let's rewrite that. F is 1 over x, so it's 1 over x squared plus 1. Phi prime, which is 2x, is equal to phi of 0, which is 1, phi of 1, which is 2, f of x, which is 1 over x, and then dx. And then now we're going to have to use the first fundamental theorem. So first fundamental theorem tells us this is natural log of 2 minus natural log of 1. Or you could even just use the definition of natural log. So that might be easier. This is natural log of 2 by a theorem, I guess. That was like how we defined natural log of 2. So the answer would be natural log of 2. Okay. So this brings me to the end of this video. So this also brings us to the end of the discussion on integrals. So next time we're going to start talking about Taylor polynomials. So I will see you in the next video.